Okay, welcome to the lesson on the number e. Yep, the number e, not the letter e. So we're going to learn a new number today. So what we're going to do is we're going to start by looking at an exponential function. We're going to look at the function y, nice y, equals 2 to the power of x. So you should know what that looks like. Something like this. So really what our goal is actually going to be here is to find the derivative of this. But what we're going to start with is actually we're going to look for the slope of the tangent to this function at a specific point. So we're going to pick that point x equals 0. That was supposed to be a different color. Oh well. So that's our question. What is the slope of the tangent at x equals 0? So how do we get the slope of the tangent? Well, we know that the slope of the tangent, really that just means the derivative at 0. So we don't have a rule for the derivative of this. So what do we have to do when we don't have a rule? We have to use a definition, or sometimes we'll call that first principles. So the limit as h goes to 0 of quotient f at, now normally we'd have f at x plus h, but here we're given a specific x equals 0, so we can say 0 plus h minus f at, and again normally it'd be f at x, but when you're talking about a specific value, it's f at 0 all over h. So now we'll use the function 2 to the x. So limit as h goes to 0 of 2 to the 0 plus h minus 2 to the 0 all divided by h equals the limit as h goes to 0. So now we want to simplify this a bit. So 2 to the 0 plus h, okay, that's not hard. 2 to the h, 0 plus h is h. Oops, sorry. Erase. Brush. Minus 1. 2 to the 0 is 1. All over h. So now the question is, how do we evaluate this limit? And really, we don't have any methods to simplify this limit. If you think about what we used to do to simplify limits, things like rationalizing, expanding common denominators for rationals, it's just not going to work for an exponential. So we don't really have the tools to evaluate this limit. Sort of our best method at this point is really to just kind of approximate it, and the way you approximate it is by doing the table. So we're saying what's the limit as h goes to 0, so we'll just take small values of h, let h go to 0, and see what this approaches. So you take like 0.1, 0.01, 0.001, and smaller, and you see what this approaches. So I'll leave that to you. If you want, you can use a calculator to put these small values of h in here and see what this approaches. I'm just going to kind of give you the answer. This actually approaches 0.693, and it's a repeating decimal which approaches, but to 3 decimal places. It's approximately equal to 0.693. Okay, so slope of this tangent to y equals 2x at x equals 0 is 0.693. Okay, that's nice. What turns out it's actually going to be nice if we could find the exponential which has the slope of the tangent of 1. So this is too small. 0.693 is much smaller than 1. We want a steeper line. So we want the exponential to have a... let me get a different color this time. We want the exponential to have a slope which is a little bit steeper. Let's say that's 1 right there. Right? So it's a little bit steeper than y equals 2 to the x. So what we're going to do is try another exponential. So this one was too small, so what exponential might you try next? So y equals 2x was too small, so let's try one that's a little bit steeper at that point. For example, the next sort of one you'd probably think of, y equals 3 to the x. So this one is... So it's... well, I don't know what that slope is, so that's what I'm actually going to try to do that. So I want f prime at 0 for this function, y equals 3 to the x. So you're going to do the same thing. Limit as h goes to 0 of f at 0 plus h minus f at 0 all over h equals, and then if you sub in, or if you use this as your f, 3 to the x, you're going to end up with this limit. I'll skip a couple steps, but it's the same as that other calculation. You're going to end up with 3 to the h minus 1 over h. So the same issue arises. We can't evaluate that limit. The only sort of tools we have at this point are to approximate it by taking smaller and smaller values of h. So 3 to the h minus 1 all over h, and 0.1, 0.01, and so you could use your calculator, sub in these values of h, and kind of see what it's going to. And again, I'll leave that to you to do, and I'll just kind of tell you what it's approaching. This one's approaching the number 1.098. So that slope is a little bit bigger than what we wanted. So this must be a little bit steeper than that red one I drew. So there must be some exponential in between y equals 2 to the x and y equals 3 to the x. So I'm going to try it in between, where that tangent has a slope of 1. So there's some... maybe I could type this. Potential with a slope of tangent at x equals 0 which is 1. Okay, so I'm going to start a new page just to... and, well, okay, what do we know about this exponential? We know the exponential must be between 2 and 3. And actually, if you look at, this was 0.693, this was 1.098, probably suggests it's a little bit closer to 3. Nope. So, guess what? That number is going to be the number e. The number e is the number such that so we'll write it formally with a limit such that the derivative at 0 is, well, what's the derivative at 0? We said it's going to be the number such that the derivative at 0 is 1. Right? We want it to have a slope of a tangent at 1. So if we want to write that with a limit, that that means the limit as h goes to 0 of e to the 0 plus h minus e to the 0 all over h is equal to 1, or, simplifying that, limit as h goes to 0 of e to the h minus 1 all over h is equal to 1. So that's how we're going to define e. The number such that this limit is true. So the slope of the tangent is 1. And it turns out, if you were to actually evaluate this limit, or try to figure out what that number e is that works, this number e is equal to 2.718, and then it repeats. It's a repeating decimal. It's one of those irrational numbers. And this turns out to be a very, very important irrational number. Kind of think of it like pi. It's a number that repeats forever, goes on. There's no repeating pattern in the decimal. And we give this number a special name. Call it Euler's number. So that's spelled totally not how it sounds. It's spelled E-U-L-E-R. Euler number. So Euler is he was a famous Swiss mathematician. He's actually probably one of the most famous mathematicians. Might have contributed more than any other mathematician in the history of, I don't know, the world, I guess. So we read that like Euler, the Edmonton Oilers, because he was Swiss. You don't pronounce things the same way. Okay, so that's what Euler's number is.